Welcome to G Fun Facts Online, where we get curious about the world. What if I told you that the most brilliant, shimmering colors you've ever seen aren't made of paint or dye at all? Imagine a color that never fades, born not from a chemical, but from the very shape of things on a microscopic level. We're talking about the dazzling blue of a Morpho butterfly, the metallic sheen on a beetle, and the fiery flash of an opal. This isn't magic. It's a phenomenon called structural coloration, and it's about to change our world. While scientists like Robert Hooke and Isaac Newton first noticed it centuries ago, we're only now starting to unlock its full potential. So how does nature paint with light itself, and how are we copying its secrets to build the future? Let's get into it. First, we need a quick science lesson. Most colors we see every day, like the color of your t-shirt or the paint on your wall, are pigmentary. This means they contain molecules called pigments that absorb certain wavelengths or colors of light and reflect the one we see. A red shirt looks red because its dye absorbs all the blue, green, and yellow light and only bounces the red light back to your eyes. Structural color is completely different. It has no pigment to absorb light. Instead, it uses microscopic, intricate structures. We're talking nanostructures, things smaller than a wavelength of light, to literally bend, scatter, and interfere with light waves. Think of it like this. Pigment color is about subtracting light, while structural color is about directing it. When light waves bounce off these tiny structures and line up perfectly, they amplify each other, creating an intensely vibrant color. When they're out of sync, they cancel each other out, erasing other colors. This is why structural colors are often iridescent, meaning they seem to change as you move your head. It's all about the angle. Nature has been the master of structural color for millions of years, using it for everything from camouflage to attracting a mate. One of the simplest examples is thin film interference. You've seen this in soap bubbles or a slick of oil on water, creating that rainbow sheen. It happens when light reflects off both the top and bottom of a super thin transparent layer. In nature, this gives buttercup petals their glossy shine. Then you have diffraction gratings. This sounds complex, but you've seen it on the back of a CD or DVD. It's just a surface with a series of perfectly spaced parallel grooves. When light hits these grooves, it scatters into a rainbow. A peacock's feather is a perfect example. Each barb is covered in tiny ribbed structures made of chitin and air that act as a natural diffraction grating, creating that mesmerizing shimmering display. Maybe the most extreme example is the sea mouse, whose bristles form a structure that acts like 88 diffraction gratings stacked on top of each other, creating a warning signal of incredible vibrancy. Scattering is another major mechanism. You know how the sky is blue? That's Rayleigh scattering. Tiny particles in the atmosphere scatter blue light more than other colors. Nature does this too. The waxy coating on a blue spruce tree uses the same principle. But when the scattering particles are arranged in an orderly way, you get what's called coherent scattering. This is the secret to the bright, non-iridescent blues you see in the feathers of many birds. The structure is just ordered enough to produce a consistent color from any angle. The most complex form of structural color comes from something called photonic crystals. These are 3D nanostructures with a repeating pattern that essentially creates a bandgap for light, forbidding certain colors from passing through, and instead reflecting them with incredible intensity. Precious opals get their fire from this. And the most brilliant blue known in any living tissue belongs to the marble berry. It uses a spiral structure of cellulose fibers to create a blue so vivid it looks almost unreal, and it does it all without a single drop of pigment. This is amazing in nature, but the real revolution is happening as we learn to copy these designs. The applications are mind-blowing. Think about paints and coatings. Companies like Cypress Materials are developing paints that mimic the Morpho butterfly. They start as a clear liquid, but as they dry, polymers self-assemble into nanostructures that reflect a specific, brilliant color. A color that will never fade from the sun, because there's no pigment to break down. This could lead to cars, houses, and close with permanent color. Researchers have even created an ultra-lightweight structural color ink that could save huge amounts of fuel if used on airplanes, just by reducing the weight of the paint. The cosmetics industry is also jumping in, using plant-based cellulose to create dazzling, iridescent makeup that's non-toxic and eco-friendly. But one of the most powerful applications is in security. Because iridescent structural colors are angle-dependent, they are incredibly difficult to copy. This makes them perfect for anti-counterfeiting features on banknotes, passports, and credit cards. We can even design them to be hidden, only appearing when triggered by something like water or a specific type of light. And it gets even better. Because these structures are physical, we can design them to change. Imagine a medical bandage that changes color to tell you a wound is healing properly, or a food package that signals when the food inside has gone bad. Scientists are developing flexible structural color materials for chameleon-like soft robots that can change their appearance on the fly, and for next-generation displays with unbelievable resolution. Of course, there are challenges. Manufacturing these precise nanostructures on a large scale is still expensive. But with new techniques like roll-to-roll nanoimprinting and 3D printing, we are getting closer to making structural color a part of our everyday lives. The future of color isn't being mixed in a bucket. It's being built, atom by atom. We are learning from nature to paint our world in a new light, one that is more brilliant, more durable, and far more sustainable. Thanks for listening to G Fun Facts Online.